On the 19th of June, the OceanGate submersible began its descent to the Titanic's fractured remains here in the northwestern Atlantic. With a descent rate of 55 meters per minute, it would take the submersible 70 minutes to reach its destination. With each passing minute, the equivalent of 5.3 atmospheres of pressure would be added to the sub's hull. By the time it reached its target depth, the weight of 366 of Earth's atmospheres would be attempting to crush it. Applied to an area a little larger than an A3 piece of paper, that's equivalent to the thrust of a Saturn V F1 engine, pressing in from all directions. An hour and 45 minutes into the dive, at the bottom of the ocean, 3,800 meters down, with this immense pressure bearing down on its hull, the OceanGate submersible lost contact with the surface. We now know the submersible imploded, a sudden catastrophic collapse, a tragic accident. However, any composite material engineer could have predicted this failure, and they did. I worked as a composite design engineer and completed my master thesis in composite failure prediction. So, let's dive into the questionable engineering decisions that OceanGate made that led to a tragic accident. With that pressure comes some extreme design challenges. OceanGate's Titan submersible consists of two titanium end caps, one with a large acrylic window, joined to a filament-wound carbon fibre reinforced epoxy hull. Inside the submersible is pretty bare bone. Some screens that are fed data from cameras from the outside, and the 4 electric thrusters are controlled with, from what I can tell, a third-party GameCube controller. Many people are focusing on this part of the design, but that's the least of my concerns. We will be focusing on one design aspect of this submersible, the composite hull. Carbon fibre composites aren't really known for their compressive strength. They work best in tension. Great for aeroplanes that are pressurized from the inside, where the pressure inside the fuselage works to expand the circular cross-section, putting the fibres in tension. For a submarine, the pressure will work to compress the hull, placing the fibres primarily in compression. This immediately set off alarm bells in my mind when I heard of the missing submarine, so I began digging into their justification for using the material. OceanGate chose this carbon fibre composite primarily to benefit from its natural buoyancy. These type of subs actually want to be as close to neutrally buoyant as possible, meaning the weight of water they displace weighs about the same as the vehicle itself, minimizing the energy needed to rise or sink in the water. This means to surface in an emergency, they don't need power, they just drop ballasts that make them positively buoyant and they just float to the surface. The carbon fibre composite can be lighter and thus helps achieve this neutral buoyancy target. Typically, submarine hulls are made from steel or more recently titanium, but in order to achieve the desired buoyancy, they need foam outer layers. OceanGate's CEO, Stockton Rush, who was inside the submersible, stated that they wanted to skip this foam layer because it added to costs. That isn't necessarily an evil thing if the composite is up for the job. This is where things get iffy. OceanGate had no idea whether it was up to the task or not, and we know this because they admit it in their own blog post, justifying their decision to not test the vehicle with a regulatory body. The now removed blog entry reads, "Most marine operators require that chartered vessels are classed by an independent group. Classing assures ship owners, insurers, and regulators that vessels are designed, constructed, and inspected to accepted standards. Classing may be effective at filtering out unsatisfactory designers and builders, but the established standards do little to weed out subpar vessel operators. The vast majority of marine and aviation accidents are a result of operator error, not mechanical failure. As a result, simply focusing on classing the vessel does not address the operational risks." Now, I would have thought this wouldn't need pointing out, but the fact this glaring red flag has been written on their own website for everyone to see, and several extremely wealthy and successful people didn't seem to think it was an issue, seems to suggest otherwise. Perhaps most submarine accidents occur due to operator error, precisely because they have undergone rigorous testing and certification. The comparison to aviation is just a wild can of worms that we have very recent catastrophic accidents to compare to, where manufacturers willfully circumvented regulatory procedures. These aren't procedures created as some kind of unnecessary inconvenience to inventors. They are very useful guidelines and testing procedures to prove that you've not missed some catastrophic failure mode in your design, and that's exactly what happened. One failure mode is unique to composite materials in deep-sea applications. Some of the first evidence we got for it was in glass fiber reinforced deep-sea piping. It's called snap buckling or delamination coupled buckling failure mode. For thin-walled pressure vessels, the failure mode is simply buckling, where the pressure simply caves the entire wall in. But here, because the wall thickness is so large to deal with the immense pressure of the deep sea, the failure mode gets more complicated. This failure mode is characterized by delamination of the internal layer of the pressure vessel. Basically, the inside of the pressure vessel suddenly peels away from the rest of the wall, leading to a catastrophic failure of the overall structure. The exact mechanisms of this failure mode are not entirely well understood, as stated in this 2022 research paper titled "A Review of Structural Failure of Composite Pressure Hulls in Deep Sea." It states in its conclusion, investigations on this subject have remained at theoretical level. There is still very little research in this area in recent years. So, I am assuming whoever engineered this pressure vessel did at least the same level of research as a YouTuber who wrote a script on the subject in 2 days. They must have at least been aware of this problem. A failure mode like this is going to be exacerbated by gradual damage incurred by cyclical stresses, like those experienced when diving to depths of 4,000 meters and resurfacing again. They have done that at least 50 times with this vessel, without ever fatigue testing it. Per their own admission, they did not undergo industry standard classifications, but they did do their own classification test. One test, stated on that blog post once again. A licensed marine surveyor will witness a successful dive to 4,000 meters, inspect the vessel before and after the dive, and provide a statement of fact attesting to the completion of the dive test plan. That is simply not adequate. Anything undergoing repeated stress cycles like this needs to be fatigue tested, like the test airplane manufacturers do on wings, where they flex the plane's wings thousands of times on the ground. They designed this thing essentially with computer modeling, with no real-world testing. Composite materials are incredibly difficult to model in computer software. Composite materials are far more complicated than homogeneous materials like steel, where the material properties are the same in all directions and in all regions of the material. Composites are composed of fibers bound together by a matrix material like epoxy. If we were to zoom into a small cross-section of this, we may see something like this. Some fibers, some of them could be touching without any matrix between them, some could be spaced further apart, and there can also be empty voids that the epoxy didn't manage to fill. We can simulate a small section like this independently to help analyze some failure modes such as delamination. However, if we want to zoom out and test a larger section, we often need to average the material properties in some way, or else the simulation will take too long to run. My own master thesis tried to combine the two by embedding a fiber and matrix cell within an averaged composite material. There are specialized softwares that can model different fiber orientations, but they are still very much an estimation. You need to back this up with physical testing, something OceanGate didn't do. There are more signs of incompetent use of composites. For a critical structure like this, I would very much recommend curing it in an autoclave. That's basically a pressurized oven that helps push those voids I mentioned earlier out of the epoxy resin. Autoclaves are expensive, and it can be difficult to find ones large enough to fit something like this, but it's nice to not have air bubbles in a pressure vessel keeping you alive. However, an autoclave was not used for this pressure vessel. It was simply bagged and cured, a cheaper alternative. Spencer Composites was commissioned to make the composite hull, and their CEO was interviewed back in 2017 in a Composites World article. He seems very aware of the immense design challenge he has been handed, and he does mention that the porosity of the cured pressure vessel was assessed to be less than 1%. Less than 1% voids doesn't exactly inspire confidence. Is it 0.99% or is it 0.001% porosity? That's exactly the type of defect that's going to increase the risk of snap buckling, as voids can be a propagation site for delamination. The blog post goes on to dismiss classification tests as unsuitable for innovative designs, which is complete narcissistic nonsense. This isn't innovative. They have made a pressure vessel from a carbon fibre composite using known manufacturing practices and started charging rich people $250,000 to risk their lives in it. Innovation would be creating that pressure vessel and testing it, figuring out the causes of snap buckling and advancing material science for all mankind. This is profiteering, not innovation. To eliminate all doubt that this company has willfully ignored safety standards, this court case from 2018 was brought against OceanGate by a former employee who was fired shortly after raising concerns about the composite hull, stating that not enough was done to check for delaminations and voids. OceanGate argued that the technology to check for voids and delaminations in a composite this thick did not exist, and instead they would use their acoustic monitoring system, which essentially listens for the sounds of fracture to predict failure. But this is what a carbon fibre composite fracture curve looks like. It's a cliff edge, sudden, catastrophic collapse. An acoustic monitoring system like this is akin to setting up a camera to warn you thunder is coming. You will see the lightning before the thunder, but the time between them is minimal. This is pure safety theatre. It gets even worse. On one test dive in the Bahamas, a submersible expert could hear the cracking with his own ears and warned Stockton Rush that it was a sign of damage accumulating. Stockton, once again, chose to ignore an expert's advice. So, this acoustic monitoring system was purely for marketing purposes, to give customers who don't have the engineering background to see through it a false sense of security. I would attribute this to malice and greed, but Stockton Rush chose to pilot this death trap himself. As Hanlon's razor goes, never attribute to malice that which can be attributed to stupidity. There is a growing trend in engineering of moving fast and breaking stuff, mostly driven by one overconfident CEO who has, to be fair to him, succeeded in revolutionizing an entire industry with that ethos. That incriminating blog post even mentions SpaceX, Blue Origin, and Virgin Galactic as bastions of innovation for this move fast and break things mantra. Virgin Galactic too have blood on their hands, with their 2014 in-flight breakup, which was attributed to inadequate design safeguards and poor pilot training, along with the lack of oversight from regulatory bodies. This attitude is dangerous, and this won't be the last story of wealthy, narcissistic CEOs putting lives at risk. When a doctor is negligent to the safety of their patients, they are liable for malpractice, but the impact their incompetence has can affect one patient. When an engineer neglects their responsibilities, it can affect hundreds, thousands, maybe even millions. We need more people like David Lockridge, the employee who was fired for raising concerns over safety. The very first video on this channel stated our mission: to inspire the next generation of engineers. But it's about more than just inspiring engineers. We need engineers going into the most impactful industries to solve the largest problems facing our civilization. You've probably heard a lot of career advice. Follow your passion, do what you love, take initiative. But a lot of advice out there doesn't take into account the best available evidence we have for what actually makes for a high impact and fulfilling career. Today's sponsor, 80,000 Hours, is a non-profit that, for the last 10 years, has been researching the question of how you can find a fulfilling career that does good too. Everything they publish is based on careful consideration of the data, consultation with experts, and taking into account the best evidence they could find on the topic. And because they take this evidence-based approach, they are able to make concrete recommendations on hard questions like, where should I work if I actually want to make a positive difference in the world? What are the most pressing problems facing humanity today, and how might we solve them? And what can I do today to start planning a fulfilling career? They have published over 30 articles on one incredibly pressing issue: safety in the development of AI. They have a website with tons of collected research on high-impact careers, a job board which lists currently open roles they think might help you have a positive impact, and a podcast where they have conversations with experts about the world's most pressing problems. Everything they provide is free, forever, because they're a non-profit. Their only aim is to help solve global problems by helping people find the most impactful careers they can. If you join the newsletter now, you'll get a free copy of their in-depth research-led career guide sent to your inbox. Just sign up to 80,000hours.org/real engineering or click on the button on screen right now.